Also, it's the team 6 deep learning project where we are taking the Kaggle project wildlife image classification and counting the images. This is the Kaggle competition from iWildlife 2021. Harpreet will start.
Let's move on to the next slide.
Yeah.
Thanks. So we've learned a lot of convolutional networks, right, Deepak, from you over the last 8 weeks. So what we wanted to do was explore one pass pipeline versus multiple pass pipelines, because we could recognize you're a big fan of YOLO and we wanted to try what's so great about YOLO. And then the other models that we've learned over time, right? The convolutional network models. The other thing that we also thought was, in other courses, right, we did a lot of ensembling and we said ensembling helps. While there is some ensembling when you do CNNs, right, you create more filters, you need more kernels. So you try to extract more from the same filter by using different kernels. But what we thought is it possible that different models, different pre-trained models, if I combine two different models, would I get better results or not? Is it worth it or not? And then finally, we also wanted to figure out the impact of bias in CNNs, right? In terms of the training bias that will creep in. And we'll talk about it on the next slide as to why we did that. But as a part of the data set that we had, we got a gold mine of data. So this data was actually from the wildlife data set on Kaggle, had a lot of images on of wildlife across multiple national parks. Now, each image could have an animal, could not have an animal. It could have one animal, it could have multiple animals of the same type, and so on and so forth, right? And the objective within Kaggle was to count the number of animals in an image. We didn't go down that path. We said, let's take that data and try to frame our own problem. Yeah, next one, Ram. So in the overall data set, we had about 200,000 images from 323 locations, right? 60% of these images were blank. And out of the 40% that had images, right, which means about 80K had images, but 80K images had about 173 animals. So, and there were 197 categories of animals spread across different time of the day and different months of the year. So the snapshot here actually talks about this, right? Saying these are the patterns that you see in terms of vegetation, in terms of just some parts of the animals being visible in the picture and so on and so forth, right? So depending upon this data, we actually formulated our problem. Next one, Ram. So what models do we use to do this convolutional network? We said, let's try a couple of models. So we picked upon Xception ResNet v2 with a 95.3% top accuracy. So they were just about, let's take any three models, right? So we looked at DenseNet, EfficientNet, and InceptionNet. And then we also thought, let's also try YOLO because we want to find the animal and predict it. Unfortunately, while we were doing all of this, we said YOLO takes a lot of time to train this because it is trying to do everything in one pass, right? And we needed some sort of training data to feed into YOLO with respect to bounding boxes. And there also we figured out something really great coming our way, and we'll talk about it on the next slide. Yeah. So once we got that image data set, we came across something called Microsoft MegaDetector, which is a tool for AI for the technical resources. What this does is, if you look at the image in the backend, right, it builds a bounding box on top of that image. And then you actually feed a image into it, and it gives you, it's a pre-trained model to identify animals, people, and vehicles. So we used this tool to take these images and generate a sort of training data to feed into YOLO. So that's one part that we did, right? And we'll talk about what we did there because it took a lot of time. But then after taking this image data set, we did one more thing. We looked at these cropped, the bounding boxes, cropped these images just on the bounding box so that we have an image just of the animal, and then put it in a database that we could use for our regular models. So we used these regular models and trained our models on the specific bounding box images, which means we did away with all the blank images, right? And then we also did some sort of an ensemble, right? We took the convolutional basis from two different models, readjusted for them to be able to get the right parameters in terms of the tensors, and then took them through a concatenation layer and addition layer to make sure that we are able to predict using an ensemble thing. Now, finally, we also said, because we have so much of data, that data is across wildlife parks with different vegetation, that data is across times. Let's also try to shuffle this data and then say, let me train it on data from 2 national parks and then try to predict or classify animals across all the other national parks, meaning how well does a system do. So I'm sort of introducing a bias in my training system itself, right? We also tried to introduce that bias by saying, let me train it on only daytime images and then try to figure out if it can predict images from the nighttime and so on and so forth. And we'll show you the results of whatever our learnings was throughout this process, right? Next one, Ram.
So Deepak, before we jump into the actual problem and modeling aspects of that one, like Harpreet was mentioning that this image database itself is 110 GB. So we couldn't load this one in Google Colab. We couldn't get this one out of us into any of the laptops. So the only option which we left it with this challenge is to start using Kaggle itself for doing it. And Kaggle itself is having its own limitations, not going into that limitation, but just to say that's also something which we learned over the process. The database, whatever the Kaggle project was giving it is having a different type of a data sets which we are used for it and what we got it. That is, they have an annotations which is split into 3 parts. That is trine annotations, test, and MegaDetector, each one of them in the JSON format. And what does this contains is the trine contains every file. These are actually not taken photographs from any photographer. These are taken from image traps, camera traps. So anytime there is a sound in a certain place, these cameras will take the series of pictures. So these files contains the sequence when they have taken and individual IDs in each frame they captured and location of the national park and those things and different classification of the animals and category of the animals which they belong to. So they will say sequence number 100 is for lion and their actual biological name in the category part. And test is just having a plain image and the image related details. And then the next biggest one, which we saw, it is the MegaDetector bounding boxes ones, which ran it through the entire database and kept it into the annotations. This is a MegaDetector. And corresponding for all these files, the actual images are in the images trine and test. This is not at all in the format of any of the Keras data image data sets or anything. So we have to start doing a pre-processing. The pre-processing, few things which we have done it is the creating the DFs out of it, data frames, and cropping the images and resizing it. Actually, this cropping itself is used to timeout for us, whereas it spent 14 hours in Kaggle times out after 12 hours. Took a lot of time, but we converted all the images and we cropped them into a 256 by 256 box based upon the MegaDetector's boxes, which it created for every image. And we created now this cropped data set, which is available in Kaggle. If anybody wants to run it on top of that one, they can readily use it. And we fixed it to 256 by 256, resizing every image. On top of these images, then we started going into the ensembling and individual modeling and doing it. Now we have a large database of images with almost like 197 categories of images. Each one of the, if I start giving this one for the modeling, each one taking almost like a 1 hour for the model to complete. So we took we need to keep something constant. So we kept for across the models, let's compare with the 3 epochs and train the models. Let's compare at the end of the 3 epochs, how exactly the different results will fall in. And we did in that process, all the models, we ran it and we collected data, which I'll just share in a minute. And finally, we have to do some post-processing because every image is having multiple animals or one animal we have to do. So what we did it is we aggregated based upon these IDs, whatever we got to the sequence ID, the metadata which we created in the pre-processing. We took that one, took the results from the model and did some post-processing on the pandas, and we finally gave the results. And we are using accuracy as the score of metric of finding whether the actual animal is detected or not. But this is all fine, but we were trying to do YOLO also, which Hari will be talking next, which YOLO will be directly taking the model, but YOLO doesn't follow any of the Keras architecture or anything. And how do we get the labeling? So we again use MegaDetector for doing the labeling for the mod YOLO instead of the human doing that task. We're not going into each one of these models, because some of these models we touched in the class and even in the tutorials. So I'll just walk you through what are the different models, and I highlighted some of the models, and actually we got a chance to look over the actual papers and implementation of them. So that's why I listed as a reference. So this is the first one, is the Xception RESTnet v2. Why we started from here is from Jaron's textbook as one of the comments. This is the final one. He told that the 1,000+ classes are being identified. Many of them are animals. We started with that. Our accuracy, we divided into 2 parts, 10K images. If I feed in how exactly 173K images, if I give in, we see our validation accuracy is coming to 0.19, and which almost like took 45 minutes for us to train that model minutes. And then we took, okay, which are the other models which we can see it. One thing which we were looking into the papers, and one thing is very good with the animals is they are good in nature of mixing with the whatever the environment they are in or the climate they are in. So they have a minute features which also differentiate between different animals and different species of the same kind in nature. So in that way, DenseNet, which will be keep on passing the information what it learned in one network to the next network within that one, where they're calling it as a dense blocks, and the translation layer will reduce the convolution layer accesses and will be going in. So we wanted to go with this one. This is being suggested for the animals. So we took this one. As soon as we started it, we got into the next choice of which one to train it, 121, 169, 201, 264. We selected 121, which is the faster to run and a lesser number of parameters. Our accuracy, when we compared with the full database, it improved by 3x. So we were getting 0.19, 0.2, and we were got here as 0.64. With that good start, we were started searching, is there any other networks? That's why, Abhishek.
Yeah. Hi, Deepak. So now let me introduce a superstar model here. That is EfficientNet, right? So as Ram explained, we started with a very baseline model, and then we got better with the DenseNet, and then we were looking out, right? How can we improve more? Then we kind of did some research and found EfficientNet, right? It's a very new one. I think 2019-20 Google have published this. So what is the basic funda here, right? So right side diagram says that let's say the figure A is a baseline model, any baseline model. Now what is talking about, the author talks, right, that there are 3 ways we can improve the model. Number 1 is the width scaling. What does he mean, right? That in every layer, so you don't increase the number of layer, but in every layer you increase the number of neuron. That is one way to improve your model. Another way is you don't do that, but you increase the depth of the model. So if you see what he's trying to say, that each layer is repeating one more time. In that way, it increasing the depth of the layer. And third one is you give more information, right? By giving like more resolution data. So in the case of images, you give image with a more width and height. So he's saying that there are 3 ways to kind of improve your model on any data set. But the thing is, most of the model till now, right, we were focusing on one of the approach, and paper says that actually very hard to club all these 3 and come up with the very optimal model which kind of optimizes in all these 3 dimensions. And they are saying that by doing this their research, right, they were able to kind of get this balance, and they are calling it as a compound scaling. And they are saying that if you just increase one of them, actually we hit that diminishing return, and that's how by using compound scaling they are able to get the better model. And they have a hyperparameter called phi. Using that phi, so they have taken very different approach. So generally what we other model, right, they come up with the model and then see they train on the different hardware and see that, right, okay, how much efficient it is, right? Here actually approach is very different. So approach is like resource intensive, right? So with the help of phi, you know your resources. So I have this much resource, this much the parameter I can go for, and with phi actually you can increase. So if you have more resource, you can increase more phi, and the EfficientNet, the same architecture you can scale, and it is shown that it gives better result. And internally, so this is like how what is compound, this is the main thing, how they actually improve the accuracy. Another thing is that EfficientNet internally uses MBCOM, which is actually mobile net architecture, right? Which, so it's very light on the number of parameter and even the model sizes. How it does, right? So this is so one very key important point is that generally, so it has in residual block, right, which has a skip connection. So in our normal classes also, right, we studied this. So how generally the skip connection will work? You see right top figure. So we actually feed that residual model a thick model. So it will be wide, and then internally we try to do it narrow, and then while coming out again it becomes wide. That's how actually residual, because finally the input and outputs would have the same shape. So that's how normally actually our residual block we do. They took very opposite actually approach. So when they feed very less feature map, and internally actually they scale it out, right? And then they use depth by convolution, and then finally again they shrink it. So they call it like expand, excitation and shrink. They're calling it, right? And so by doing that, right, they are able to keep the number of parameter and model size very light. So if you see the numbers also skips for it, right? So actually we got very good validation accuracy. And Ram, can you click that link?
Doesn't go.
Okay. Okay, so basically it's the same diagram. Yeah. What we wanted to say here is right side, right? So how this 5 character one works, right? So you have your resources, and let's say you want, your resource can afford only 20 million parameter. So you see any parameter you take, and let's say you draw x is equal to 20 here, then you see, right, this efficient performs better than all the models with the limited number of resources. So it's very good in terms of, if you have resource limitations. And yeah, that's it all in the EfficientNet.
So Deepak, we got almost 4x when compared with what we started on the project. So we got maybe a greedy little bit. So we started what we saw in the song prediction one also. We got a good improvement with the model ensemble. Let's try that approach. The first roadblock we got is, yeah, like we know these two guys are giving us a different dimensions. How do we do it? So we started merging by adding extra convolution layers, concatenate it, run through the flatten. Of course, we added a batch normalization to see if will it improve. Actually, batch normalization, adding it gave us a good boost on top of it. And still, when compared with the baseline of Xception plus the baseline of the DenseNet, we got a bit of improvement. Then we took the topmost two ones, which is the EfficientNet and DenseNet, we added together. The amount of accuracy which we taking for 173K images, training is not much change, but the validation accuracy got changed by 2% to 1% of the change was there. So we tried as part of this one, can we not, instead of concatenating it, can we add these two layers together? And then we tried it, but based upon the, whenever we add these things, our accuracy fallen down to below 0.5. which kind of shows that there is DenseNet and EfficientNet is trying to find out a minute features, but they're of different features, may not be exactly in the same dimensions. They are at the different places. If we combine them, we are losing those minute features of that particular animals or the classification or the thing. So addition is not working out. Concatenation is working out. So the final one, which we see the model comparison between 10K trains versus 173K, wherever we highlighted is the green ones, we can see that that's the best one. So the final one, even though there is a 2% is the difference, DenseNet plus EfficientNet is good. But like Abhishek was pointing out, the EfficientNet with B0 as the parameter, it runs quite fast and is able to give us the accuracy almost like 0.82. Which kind of, if we want a more timing sensitive one, we can go with this one, or more accuracy, which is 2% more, we can go into the other model. With that one, we have completed the Keras one, and the last one, which Harpreet will add on to this, bias.
So this is just about bias, because we wanted to see, we've learned a lot about bias, right? But in terms of very abstract terms, saying you hit the center of the bullseye and so on and so forth. So we wanted to see what it actually means in real life. So we trained the DenseNet model on 2 out of 323 locations, right? We said we created a database out of all these 173K bounding boxes that we had. So we had 173K animals, right, in the database. And we also had metadata across the 323 locations. So we just took animals from 2 of these national parks and we trained our DenseNet model based upon these set of animals. And then we validated this across the same set of 2 locations. So the validation accuracy was about 0.44, very near to what you get across the overall accuracy, right? However, if I take the accuracy, the same model, and I try to do that validation across animals from the other locations, right, which means the other 321 locations, the validation accuracy drops, right, from 0.44 to 0.34. Similarly, we also did a time-based bias to say, let's train it on daytime images and then try to look at it on nighttime images, right? So which means now this drop is pretty high, right? So if you look at the overall drop, right, it's actually gone down below 6%, which is nothing, which means these are very, very sensitive to light. So that bias impact was very, very visible in these images. Yeah, next one, Hari, you can talk about YOLO.
Thanks, Harpreet. Yeah. So yeah, we've studied in class also that YOLO can be used for object detection as well as classification. So we thought we'll give a try with YOLO as well. But one thing we faced while training YOLO is it was taking a lot of time. So with Kaggle, we saw multiple issues where we had challenges with GPU and it was timing out. So, but we still wanted to give a try with YOLO. So what we did is we took a sample of the images. We didn't take the entire 200K images. We took some around some 1,000 images for training, and that's what we did. So if you see what we did is we used the one-stage detector over here for our model in the YOLO. So if you see the model, so the first for any object detection model, right, the architecture is we have a backbone which learns the feature, and then the next part which is the more of a feature aggregator, and then the final, the head layer, which detects the bounding box and the classification. In this model, right, we have used YOLO v5, which is based on PyTorch. So in this architecture, the head part is using a darknet 53 architecture. The neck is based on a PANET architecture. The neck part does a upscaling of the features to detect small objects, right? So that's what is done in the neck part. And the final head part is the YOLO layer, which detects the binding boxes and the classes as well, right? After running, so what we did, we ran the model on 1,000 odd images, and it took around 6 hours for training the model itself. What we did is we tried unfreezing the entire 24 layers of the model, but we had some timeout issues while training. So then what we thought, let's freeze the head part, I mean the backbone part, and then let's train the rest of the part. So with that, for 200 epochs, it took around 6 hours for training. And we got an MAP of around 4.456. Then we found out something called cache option in YOLO. Then we tried with cache, where the images are all loaded into the memory. And with that, we see that there is a decrease in the time. We found around, it took around 3.5 hours to train the same model. Now, few challenges we faced were processing data pre-processing, because for YOLO to train, you need the bounding box labels. So where we used again the MegaDetector to find the binding boxes. And then the other thing was, there are few hyperparameters, but since the we had around 24 hyperparameters in YOLO v5, but we couldn't tune the hyperparameters because it was very expensive to train the data itself. Yeah. So the end result you can see of the validation data, where we got around 0.9 accuracy for the cheetah data. All right. Yeah. Ram, to the next slide. So yeah, next slide. So one thing we found out that YOLO was taking a lot of time. So then we thought, so we should explore more into some of the open source tools, or if there are any such models which are already pre-trained or on animals. So then, yeah, as Harpreet mentioned, we came across MegaDetector. So MegaDetector, and we use MegaDetector, and then on top of that, we built other models to train. So that turned out to be a good choice for us. And other thing we learned is ensemble of the models was not giving better results, right? It was giving only slightly better results, but it was taking more time actually. And the other thing is on the bias part, which Harpreet already mentioned, right? So across locality or across location, we did see that there is a bias in the training data. So that is what, yeah, that was also we came across, right? Yeah, thank you. Any questions?
Yeah. Deepak, all these data and all the trainings, all the images and the notebooks are there in the Kaggle. So because we saved all the models also, so that we don't need to train multiple times. So if you want, we can show you that particular data. That's the end of our side of the presentation. There are any questions?
Yeah, no, very good. So it's really good. Thanks for the discussion.